Okay, so welcome to today's seminar. So this is my pleasure to introduce today's speaker, Professor Adam Jakubowski. Adam is, of course, a well-known name in probability theory. He is a professor at Mikołaja Kopernikus University in Poland, and he works in many interesting areas. Broadly, I would say that he is interested in some asymptotic theory and limit theorems, and he applied this or developed different results, for example, for stochastic differential equations. Also, he very often publish on topics probability in different functional spaces and convergence, and also on dependent random variables and their limit distributions. But Adam also well known not only because of his high level of probability results, he is also well known by his contribution to profession, to probability and mathematics in general. And I could say just, for example, in Poland, he is well known that, for example, in his university, he was as the head of department and dean of his faculty, but at more international levels that he is fellow of Institute of Mathematical Statistics, and he was president of Bernoulli Society. Also, he involved in many other activities, for example, editorial boards. He is currently on editorial board, chief editor of Probability Surveys, well-known journal in our area. But also what I found interesting last year when I attended a conference in Bochum, World Congress in Bochum, he organized really a very interesting session on history of probability. And I think it's also very important for our profession to know how this profession appeared and how it's developed. So now I pass to Adam. Adam, you are very welcome.
Thank you very much. Thank you for a very nice introduction. It's for the first time I heard some such long introduction. Thank you. Thank you for invitation once again, because it's I always like to present some results that are maybe not new, as you will see, but it is only now when they got the proper understanding and recognition. So that's the reason for this talk here. Let us start with some trip to history, but of course not long, not very long. Let me remind you that the story of functional convergence was opened by Donsker, who proved the invariance principle, standing problem for some time. In a few years later, Prokhorov was able to create a general theory of convergence in distribution of stochastic processes. And here the crucial assumption was that we understand convergence in law of stochastic processes as the weak convergence of their distributions, considered as probability measures on metric spaces. This theory was really successful. Let me remind you here only two books, very influential books, by Partasarathi and Billingsley, 67 and 68. This theory became widely recognized, and there was a huge development of limit theorems, especially functional limit theorems in 70s and also in 80s. One should stress that the success of Prokhorov theory was, well, the source of this success was that there were two clear tools. The direct Prokhorov theorem, stating that uniform tightness of probability measures gives you relative compactness. That was a very efficient, first of all, mainly clear criterion what to do to get to be able to apply some compactness arguments and so on. So the direct Prokhorov theorem, and also the converse Prokhorov theorem, which was working only in Polish spaces originally, I mean in Prokhorov's paper, but then there were several problems, so it stimulated some research and people considered this as a necessary complement. It was clear that not everywhere, not in all spaces, this converse Prokhorov theorem holds. holds. This will be one of most important topics of our lecture. In fact, this is just now. The audience is consists of probabilities, so it is not necessary to recall. But just for completeness, let us say that if we are given a probability space. Topological space with some topology, say, then we say that random elements in this topological space converge in distributions if expectations of continuous and bounded functions of those random elements are convergent. This is a well-known fact, but it was assumed that this general definition should be valid also in general topological spaces, and of course it is true. But it appears that this formalism is insufficient for needs when we leave for needs of applications when we leave the area of metric spaces. And we are going to say a few words why it is insufficient, why it suffers of some drawback. Xavier Fernig, long time ago, observed, in 1967, gave an example of a sequence with values in a Hilbert space, such that it was convergent in according to this definition in distribution to 0, but this sequence of random variables lived outside any sphere. So it was just surrounding 0 in some symmetric form, but then expanding to infinity, and that is the reason this is completely it does not agree with our intuitions. We would expect that there is some kind of boundedness, some compactness of such X and so on. So this example shows that really the formalism of weak convergence is too weak. No subsequence of this Xn is uniformly tied with respect to this weak topology. And it follows, because it is convergent, weakly convergent, it follows that in this particular Hilbert space with weak topology, relative compactness, in the sense that in each subsequence we can find a further subsequence weakly convergent, star weak convergent to some limit, is a much weaker property than the uniform tightness. So this means that our lovely tool, uniform tightness, is far from being necessary for relative compactness in those Hilbert spaces. Well, one has to say that Fernig was able, in later papers, somewhere in 80s, to give necessary and sufficient conditions for relative compactness of distributions on Hilbert space were equipped with weak topology. Nevertheless, they were very specific and not easy to check. Again, tightness is a clear weak tightness, of course. That means T tau W tightness is a sufficient condition, but those conditions by Fernig were individual, created specifically to Hilbert space and so on. And of course, this is good adventure for mathematicians to look for such conditions, but not for applications. People in application, this is my impression, say that they like clear recipes, clear ideas to apply, and not to search in every space special cases, suitable cases. Well, let us just to give some frames for our talk. The problem, I would like to pose a problem. It's open, I mean, but it's not open. It's solved, but of course, it's just to answer this question. Can we define another topology on the space of tight probability measures on this Hilbert space. These are all probability measures on this space because this is the Polish space originally H, and with weak topology is using. It is not important. Can we create some topology on the family of those tight probability measures that for that both direct Prokhorov theorem holds and the converse also as well. So this converse means this is the right tightness, is the uniform tightness, is the right tool for investigation of this of the convergence in this new topology, of the convergence of probability measures in this new topology. And the answer is yes, this will be the well, the main direction of our talk during the first part. And it appears that this corresponding theory is valid in so-called submetric spaces. These submetric spaces, of course, there will be in a moment the definition of that, but I would like to stress it contains metric spaces, and the theory obtained is unchanged, remains unchanged on metric spaces, while it can be extended without practically any change to submetric spaces. And submetric spaces is a really large family of spaces. But before, we need some tool, which is also well known, but it is necessary to say, to present it here, the Skorokhod coupling, in fact. And the starting point, it is very instructive to start this part from the well-known Skorokhod representation, almost sure representation, namely, we know that the convergence of a weak convergence of distributions, that means convergence in points of continuity, implies the weak convergence in points of continuity of the left continuous inverse, generalized inverse of those distributions functions. And because we know that this left continuous inverse considered on the unit interval has distribution with given distribution function, this means that we obtained the simplest, almost sure Skorokhod representation. If x mu n distributions on R1 are weakly convergent, then there exists a probability space, in fact, interval, but it doesn't matter, and a sequence of random variables defined on this probability space such that the Yn's are distributed according to mu n's, and Yn converges to y infinity, to this y infinity distributed according to mu infinity for almost all omega, and in fact it is possible to redefine those random variables in such a way that we have convergence for all omega. So it says weak convergence is in fact the almost sure convergence being independent of the underlying space, in a sense, living somewhere in the space. Of course, this is the standard tool, well known there are basic courses. This is ingredient of basic courses as well, but it is example showing that it is possible to do that. And of course, there were developments in this direction. Hammersley, for example, obtained such a representation in 2 or more dimensions. It was not very easy task, I say, because we lose the monotonicity and so on. Skorokhod constructed the Skorokhod representation on Polish spaces. That means on separable and complete metric spaces. But one has to say that for a long time, we see 1956, this Skorokhod representation was considered as a kind of interesting but not very useful tool. And why it was the case? It was constructed for Polish spaces, while in the middle of 50s, Billingsley defended his PhD thesis, and this thesis, a part of this thesis was published in 56 in Thames, and in this paper there was a portmanteau theorem which formulated necessary and sufficient conditions for weak convergence in arbitrary metric space. So it was the impression that this is the general theory in metric spaces. Of course, we need some more assumptions, usually tightness and so on, but we have a general theory on arbitrary metric spaces, and Skorokhod remains and is related to completeness, so it is a very special tool. Of course, there were some attempts, and they were successful in extending this Skorokhod representation, but one has to say that usually they were complicated in formulations. The underlying probability space were complicated, and there was always the problems with measurability, because if we leave the safe area of say separable metric spaces, then of course everything is more and more complicated. I think that it's time to say no, it was Skorokhod representation theorem. This was the proper direction for development of convergence in distribution. And this is our aim, to restore the justice. I like this formulation, restore the justice. Of course, now we go to submetric spaces. And definition is easy. It is submetric, so there should be some metric topology at the top. And indeed, we have a topological space is called submetric if topology, the family of open sets, contains a metric topology, some metric topology. And why submetric? Why it is called? No, first intuition is clear. We have some metric topology at the top. Of course, this metric topology should be usually coarser than the original topology. Otherwise, there is nothing interesting in such. Of course, okay. Why submetric? Why this name? This name was coined, and at least I found it in the handbook on set theoretic topology. You have some coordinates, but one has to say, well, this was a topological paper, and topologists are special people. They have a metric. Instead of use it and apply it, they want to get rid of this metric and to express this property, to have some metric in terms of internal properties without metric. Our direction is completely different. We would like to use the information and the abilities opened by metric space. So I do not know many papers. There are only few papers later referring to submetric spaces. There is a huge, I advertised that there is a huge family. This is a huge family, submetric spaces. And the basic example is related to something that I would call CCSP. That means countable, continuous, separating point. Suppose we, on some topological space, we have a sequence of continuous functions, and those functions, continuous functions, should separate the points. That means if they are coincides on 2 points, then the points are equal. They identify points, simple. When we have such a family, we can define the following metrics. We see. This is just, this series is of course convergent. And the formula is perfect, is a perfect matrix because those functions are continuous. The matrix is also continuous because this is a uniform limit of continuous functions. This means the matrix is continuous. And of course, it need not determine the original topology. It's only topology, metric topology determined by this metric that is weaker than the original one. This is a continuous matrix, and therefore the topology generated by this matrix is contained in the original topology. Normally, in general, this need not be equal. So we have a really general and easy to achieve property to know that the space is a submetric space. We need only to find a sequence of continuous functions that separate points. This is a really great advantage. We shall see in the end some example, appealing example, that this is really a powerful tool to the idea of converting some topological space into submetric space. In fact, in separable Hilbert space, we have the projections on orthonormal basis, for example, and those continuous functions identified points in the Hilbert space. So of course, the convergence of coordinates does not imply convergence in Hilbert space, and therefore we see the explicit example of continuous functions that identify points, but they do not generate the topology, the original topology. Of course, in Banach spaces, the same holds. We need always some assumptions to know that the space, given space, has the conjugate is separable and so on. Let me put here two general remarks. Sorry for those remarks, but people often complain why it is weak. It does not bring such a strong information like in metric topology. Yes, that's true. But we should remember, we use Banach spaces, for example, when we need some strong approximation procedures. Yeah. When we want to get some existence, to solve some existence problems, we use weak topologies. And well, there are many examples. These are standard examples of this type. So we aim at weak topologies because, and they are usually applied in existence problems. The almost sure Skorokhod representation in non-metric spaces, in submetric spaces, in fact. It is the first result I would like to present here by myself. This was published in Theory of Probability and Applications in 1997. And it says that if we have a submetric space, and if we have a uniformly tight with respect to the original topology, the considered topology sequence or family of probability measures, they automatically, of course, tight, yeah? Then in every subsequence, one can find a further subsequence that admits an almost sure Skorokhod representation. That means we can find on some probability space random elements in this original space X with values in X with distributions P and K and such that xk converges to yk converges to y0 for each omega in tau. So this is a convergence of topological space. So let us think for a while and Okay, this is the technical remark that this theorem originally was proved under this property I mentioned before, but it is with no changes is valid in the general space, submetric space case. But we should look at this theorem as a strong form of the direct Prokhorov theorem, because it says, it gives some criterion for relative compactness, for some convergence associated to Skorokhod representation. This is a strong form of the direct Prokhorov theorem, this theorem. And this is the idea we use here. We can now formulate the topology for Hilbert space with weak topology, just this toy example to operate with some particular case, not in general, all the time in general. So what is the announced topology? If we have a submetric space and we consider the family of tight probability measures, tau tight probability measures on X tau. In many cases, this is the case. I mean that we deal with tight probability measures. Of course, in mathematical statistics, in empirical processes, there are very general constructions, but they are, one has to say, seldom they are satisfactory from mathematical point of view, but seldom applicable. There is such a book by Wellner and van der Waart, and I checked the first edition. I don't know what about second edition, but the first edition, there was a Skorokhod representation, say, in for very general setting for empirical processes, but it was used twice, not in very effective manner. So I do not question. Of course, there are more general theories, but we work with tight probability measures. Say that we have a triple arrow convergence. So it is this notation used to say it's strong convergence if on some probability space there exists a Skorokhod representation for those laws. And then the topology we are interested in is just the sequential topology generated by the convergence triple arrow. We have, of course, to say, we shall say more just to get familiar with this kind of reasoning, but let us say first that on metric spaces and on space of probability, tight probability measures on metric space, the topology, this introduced topology, coincides with the usual weak convergence. So this is something that I promised. We construct a theory that is completely analogous to metric case. So this is just nothing new in metric case. In theory, nothing new, because it says something about subsequences and about Skorokhod representation in general metric space for tight probability measures. What does it mean, sequential topology? Here I introduced some long arrow to say this is a kind of convergence, and we want to define a sequential topology generated by this convergence. A set F is closed if it contains limits of all convergence elements. If xn converges to x0 and xn are elements of n, then the limit belongs to f. We are familiar with metric case. This is exactly the same definition as in metric case, very intuitive. So this is advantage. This is advantage. Sequential topologies are advantages from this point of view. They contain exactly the intuitions we like. And of course, this is not the most general. They are specific topological spaces. But one more advantage of submetric spaces, if we have a submetric space, then the sequential topology is the finest among topologies with the same family of compact sets. Is the finest topology among topologies with the same family of compact sets. This means that if we, for example, check uniform tightness for some random elements, we get relative compactness with respect to this strongest topology, automatically strongest, finest, the finest, this sequential topology, and this is really important. And here is the promised. There was yes at the beginning of the talk. Here is the answer to yes. If we take a Hilbert space and with weak topology, then a subset of probability distributions is relatively compact with respect to this introduced topology if and only if K is uniformly tight. And we want to make some comments, just to say there is something in this theorem. It is not just it is not rewritten some well-known facts. This is really essential use of what we obtained. What does it mean, a uniform tightness of a sequence Xn of h-valued random variables? It's just that they live up to epsilon on balls, closed balls. Ball is a compact set in weak topology. So they should not go too far from the center. Yeah. So boundedness of norms is just the uniform tightness. It's easy. We have tools for checking boundedness. So this means that, of course, if you have a uniform tight, then by the presented result, strong form of the Prokhorov theorem, we say that this is a relatively compact, uniformly tight set is relatively compact with respect to this topology, this introduced topology, because it gives relative compactness for the triple arrow convergence. So one can find in Xn subsequence and the corresponding sequence such that, and let us write this exactly, yeah? Xnk has distribution yk, and for each h and omega, we have convergence. I would like to stress pentwise. I would like to stress for each a in h, there are uncountable many conditions. So there is some regularization here, serious regularization. It's not just that we take some intersection of countable sets. No, it is we obtain some uncountably many convergences, I mean, for the representation. And the converse Prokhorov theorem. Now suppose it is relatively compact with respect to our topology generated by triple arrow. Why it is uniformly tight with respect to weak topology? Suppose it is not. So we can find some epsilon bigger than 0 and the subsequence that lives with probability epsilon outside of any k. It is not written here, but it should be that, okay, k is varies, x and k. So this means it goes to infinity with positive probabilities, yes? Because of that, no subsequence of this sequence is uniformly tight. But this means that no subsequence of this sequence x and k can admit the almost sure Skorokhod representation, because we, in fact, if we have a Skorokhod representation and we have this convergence for omega fixed and for each h, this means that pathwise we have a boundedness. This is the Banach-Steinhardt theorem. In Hilbert space is a bit easier, but more or less this says those trajectories are bounded for each omega. If they are bounded, then of course we can build more and more bigger, we can take bigger and bigger balls, and then those trajectories would fall in those balls. This means if a sequence admits does admit the Skorokhod representation, it is uniformly tight. It is uniformly tight. Therefore, we see there is a converse Prokhorov theorem here. And one comment here written, it is the shape of compact sets rather than completeness. People for a long time considered Skorokhod representation or Prokhorov theorem related to completeness mainly. And of course, but in fact, it is the shape of compact sets. First, for example, in Polish spaces, this is boundedness with respect to some lower semi-continuous functionals. So this is very popular criterion, yeah. And we know in Polish spaces, if a set is totally bounded, then of course it is compact. Its closure is compact, yeah. But for example, why do I say about shape? If we take rational numbers, then rational numbers, of course, there are compact subsets of rational numbers, convergent rational sequences, and so on. But there is no general formula, general shape of a compact set in rational numbers. And a well-known price example shows that this is not a Prokhorov space. Yeah, so the converse Prokhorov theorem does not hold in for rational numbers. Okay, the stochastic compactness method in SPDs. This is very abstract so far. Of course, the Hilbert space and weak topology are maybe not so abstract. It's quite commonly used analytical tool. But nevertheless, once I presented this talk and I've got a comment, it's very abstract. It seems to be very abstract. Yes, that's true. But at the moment, there are at least 300 examples, various examples, how this method, method based on this strong form of Prokhorov theorem, how it works. And there are various areas, for example, existence of solutions to stochastic partial differential equations, existence of invariant measures, or some other existence problems. First, we check using weak criteria of compactness. Then we apply some other assumptions that to change the weak solutions into strong solutions and so on and so on. Standard methods, of course, very specific to each particular model. You can study such results. It is possible to see, for example, on Google Scholar to list papers where this method is used, not cited. It's used. So this is the main advantage. And if you want to learn more about convergence on submetric spaces, please, this is freely accessible review or the surveys paper published in some open access journal. So it's just an introduction to basic things without proofs. We shall discuss some highlights. It's at least 15, at most 15 minutes left. So we have to list some topological properties of submetric spaces to convince you this is the really tool we can use. What does it mean? Submetric, I recall, if tau contains a metric topology, tau m, equivalently, it is possible to express this property. If there is a matrix which is separately tau continuous, that means one argument is fixed, it should be a continuous function on the other. So this can be reduced to this point, but of course it is not. so important. This criteria, it's usually we see that the metric is continuous or not. Of course, the metric topology provides Hausdorffness, so they are Hausdorff spaces. Compact subsets of submetric space are metrizable, and moreover, a subset is compact if and only if it is sequentially compact. It is not all those problems, Tikhonov theorem and so on, they do not exist in our case. In submetric spaces, if we have this one matrix, continuous matrix, then compact sets are sequentially compact, in fact. So this is a big advantage. Okay, this is not surprising because we have some minimal property of compactness. Okay, and this says that if we have two topologies and one is stronger than the other, and this is the one that the lower is compact topology on some set, so the other coincides. So we have some minimal property, and this is the result, of course, after some work. In submetric spaces, the closure of a relatively compact set coincides with metric closure. That means we have to add limit points and consists of limits of convergence sequences. Warning, the closure need not be compact. No, this is the pathological situation. For example, it is the most simple case is Smirnov K-space, where we remove one convergent sequence from usual topology, and then we get the non-regular topological space. But this is a submetric space, still submetric space. But this is really not a problem, because in most cases we know what does it mean tightness. Tightness is given by some conditions, some boundedness. So if we take the closure, then of course the closure also usually satisfies those conditions, and therefore is closed and relatively compact. That means a compact. So this is not a real problem, but checking uniform tightness requires some care. Okay. We stated that this is a topology. We introduced a new topology on this space of tight probability measures. So let us answer yourself, what does it mean that xn mu n converges in this topology to mu infinity? This seems to be the obvious answer. It's triple star convergence. No. What does it mean that we have a convergence in topologies, that in each open neighborhood there are almost all elements of this sequence, and this is not triple star. In general, triple arrows, converges implies this convergence, but not conversely. But we have something that I used to call Kisinski's recipe, that says we have convergence in this sequential topology if and only if in every subsequence one can find a further subsequence converging in the sense of triple arrow. Of course, this looks complicated, but we are familiar with such things. For example, we know that convergence improbability of usual random variables holds if in every subsequence one can find a further subsequence such that this further subsequence converges almost surely the limits. So we know this kind of reasoning. Convergence improbability is obtained from almost sure convergence exactly the way that our topological convergence is obtained from convergence triple star. So to express this for random elements, a sequence of random elements with values in submetric space converges in law if and only if in each subsequence or every subsequence one can find a further subsequence admitting an almost sure Skorokhod representation. It's completely sufficient for applications. In fact, this was invented long time ago, this kind of convergence, exactly 30 years ago, in 94. Then I submitted this paper to some volume devoted to Skorochod's ideas in probability theory that was supposed to be published, but it was published after 5 years. No, this was the problem of transformation in Ukraine. So that was the unfortunate event. So it is unknown. This idea of this topology is unknown. That's one of the reasons I used to tell this story about this. One more illustration of our techniques. Space of measures as a submetric space. We have a submetric space, and take some metric that is compatible. That means topology generated by rho is contained in tau. This matrix generates Prokhorov's matrix on the space of tight, in our case, tight probability distributions. We are not interested in properties of this Prokhorov metric, whether it's complete or not. No, it is a matrix on the space P. So, in fact, because this matrix is corresponds to convergence in distribution, but with respect to metric topology, so this is weaker than our triple arrow convergence, and therefore this is a space of distributions with our topology is a submetric space. So we can consider, for example, random elements, random measures, or conditional distributions as elements of some submetric spaces. It's well, usual situation, but very convenient situation. And the final example we shall present, of course, not in details, because this would require some more lecture, another lecture, non-Skorokhodian topology on the Skorokhod space. Consider two quite natural conditions. Well, considered, for example, by Stricker in the middle of 80s. Suppose that we have two conditions: a subset of Cadillac functions. Should be uniformly bounded and should have bounded numbers of upcrossings from below A above B. No standard notion in the martingale or semi-martingale theory. So the K should be bounded, uniformly bounded. Every such functional should be bounded on K. So these are two conditions, say. In fact, it is possible, of course, they will be criteria of compactness, and we can look for convergence for those conditions for this convergence, those conditions should be the criteria of compactness, relative compactness. And in fact, it is possible. We have such formula. This says xn converges to x0 in S if for every epsilon we can approximate original sequence with some elements of finite variation, and those approximation, this is a uniform approximation, and this approximation should be convergent in fact star weakly to weak star topology on functions of finite variations, which are in fact the continuous functionals over continuous functions on 0, 1. Yeah, so we have a such convergence. It looks complicated, but it is very informative. It is possible to derive interesting consequences of this convergence. we have defined criteria of compactness and a suitable convergence. And in the next step, we should consider some topology. This topology will be called S topology, non-Skorokhodian S topology, on D as the sequential topology generated by this convergence. Sequential topology generated by this, but not enough. It is not enough from the point of view of formalism, probability formalism. Sequential topology, well, does not fit to the general scheme. Completely regular topological space, metric space, and so on, but not such simple. But we can convert our space with this sequential topology into submetric space by choosing a family of continuous functions according to the recipe presented before. So the mapping that can be used as the continuous function separating point in the standard. This is just integral over some intervals u plus delta normalized. This is clear that for right continuous functions, when we go with delta to 0, this is converging to x u. So this is a sequentially continuous. They are sequentially continuous functions and they separate points. We are obtaining the CCSP property, and this means that we have a submetric structure on the Skorokhod topology. In fact, we have a very excellent situation, namely those random variable, those functions are very close to projections. So the sigma algebra of Borel sets with respect to this S topology is exactly the sigma algebra generated by Skorokhod topology. And in fact, this topology, S topology, is something that is just below. There is nothing above S topology, just below topology, just below the J1 topology or M1 topology, in the sense that it has some continuity of addition, but in sequential manner. This is not the usual continuity, but nevertheless, this is the finest topology below J1 that addition is continuous. And final remarks, all that was done in the middle of the 1990s. This is exactly what I wanted to stress. There was no formalism. The formalism was invented. Now this formalism is recognized. I presented some, well, I did not present any application, but I said there are 300 papers using the formalism of the Skorokhod representation in non-metric cases. And also this non-Skorokhod topology was used by many people. It was published in Electronic Journal of Probability and was fully recognized long later, 15 years later, I would say, as a really good reference, presenting the variety of results and quite interesting application of the S topology. I would recommend to the audience the paper by 4 authors mentioned here: martingale optimal transport duality. This is really this is something I am proud. Without S topology or without something substituting for us, it wouldn't be possible to prove this theory, that this paper or the theorems from this paper. And one has to say that this seems to be a crowning, finishing this direction of optimal martingale optimal transport results. Okay, so this is the end of my talk. Thank you for your attention.
Thank you, Adam. Thank you, Adam, for very nice historical overview and connections to what is done now. So if you have any questions, please unmute yourself and ask. Adam, I have a quite general question. Is it possible to move further than submetric spaces? Or this is like the largest, in some way, class where you can expect this type of convergence results?
No, yes, of course you can go. You have a submetric space is not, for example, need not be completely regular. So, for example, you can consider completely regular spaces, and they will not be submetric. I mean, but really the property that compact sets are sequentially compact and they are metrizable, it seems that this is really suit for needs of probability theory. This is the best formalism for general consideration in probability theory. Of course, perhaps in some very special topics and so on, you need, but this is the really efficient and easy in manipulation tool. Yeah. When you want to check some compactness or uniform tightness, and in very general cases, okay, it's compactness when you have to use, as I said, Tikhonov theorem or something like that. This is the useless from the point of view because we are working with countable many conditions usually, yeah, in probability theory. This is the language of countable many conditions of tightness and so on. So this is the, in my opinion, this is the best when you want to operate easily. And let me stress this once again. Those 300 papers, more authors, those 300 papers use this formalism because it is really natural and easy. It remains as if it were the metric space, I mean. And then they can, for example, consider a really complicated model in some SPDs. I saw some papers with product of 7 spaces in each weak topology, in some strong topology, but they are still, such products are still submetric. So this means this formalism can be used, and really then they can pass to almost sure a convergence, and to have that along watch each omega, they have a convergence in 7 topologies at once. Yeah. So this is the really efficient tool. So they this is the reason that this formalism was accepted by most people in this particular SPDS theory. We cannot expect thousands of citations because it's to apply such formalism you need some knowledge, you have to apply some machinery and so on. This is not accessible to everybody.
Okay, thank you.
I have a question.
Please.
Hi, Adam.
Hi, Benjamin. Ben.
You showed us this nice example of Hilbert space with weak topology, and then it fits into the theory. And you can extend it, of course, to dual spaces of separable Banach spaces. Can you go, yes, does the theory work in other situations? If you take, say, L1 space with weak topology, can you...
No, it's everything depends on whether you can find this countable family of separating spaces. So not always it works. Yeah. It's not just too bad. There are no, but usually such topics are more difficult. Of course, if you have if you think purely analytically, then of course it does not matter to you. But in this particular case, you have to assume something that allows you to reduce to the real submetric case. I mean, so this is not always will work. Yeah.
Okay, thank you.
Okay, any other questions or comments, please?
I have a question here. The probability is actually a mass of one distributed over some carrying set. So given what I understood here, looks like you can do the mapping from 0, 1 to this whatever valued space. Well, what is proper, say, carrying set? How large is the carrying set that you have to have this set? If it's smaller, then you lose probability 1. So you take a chunk away from there. So is there such a sort of structural study on the carry subset of whatever space you have, right? And so the actual probability is carried by a subset in there.
No, I did not go in sub probability kernels and so on. It's the area is open for research first. The second is we have to be able when the basic idea here is to have the uniform tightness. Yeah, so even with smaller probability than 1, but the whole measure should be concentrated, almost concentrated. All measures should be almost concentrated on compact sets. Yeah, and compact sets are more or less similar. I mean, that means it's if you embed them in one space or in the other space, they are often isomorphic and so on. So this is the fact that probably this formalism can work not for probability, but the uniform tightness assumption is essential. Without that, you cannot do anything. It's my impression.
All right. Okay, thank you.
Okay, thank you. I suggest that we probably stop now. Thank you very much, Adam, especially for very early time in Poland and for everybody.
Not very,
Yeah, not very.
I was able to get it.